clap, it's okay, yeah. Thank you, Adam, very much, and thank you to Christian and Dima for requesting this workshop and for helping us to organize it and to give us so much support. Thank you for IPAM for hosting us this week and for facilitating collaboration and innovation across disciplines. It is an incredible privilege to be here today, and it has been an incredible privilege to have participated with IPAM over the years. I was looking over the topics that were suggested for this workshop. I was looking at all of the talks that you all have submitted. And overall, we have these recurring themes of course, artificial applications to global weather and climate simulation, or as we called it for this workshop, Earth system simulation. Mathematical operators for complex dynamical systems, the mathematical structure of Earth system data, ML applications to atmospheric physics, microphysics, different hazards, and uncertainty quantification. And it's so interesting to see these themes arise from when we originally proposed this workshop. We had a very different idea of what was going to happen in science at that time. And between then and now, things have evolved so beautifully that it is such a surprise to see all of the talks that are here today, and we're so excited to learn with you. The work that I'll present today is representative of the work of a broad community of NASA scientists and collaborators who have contributed to the development of machine learning applications in Earth system variability. I'm presenting the material today, but many of these ideas and the results and the figures originate from colleagues across multiple teams and disciplines. I have a disambiguation slide for myself because I found, unfortunately, that I need it. Many of you probably don't know me. My name is Katherine Breen. There is actually, for the first time in my life, another person with my exact name at my organization. Not only does she have my exact name, we work in the same building, on the same floor, and she also does machine learning applications in Earth system science. So it has caused some glorious confusion. To introduce myself, I first attended IPAM as a graduate student for several long programs, actually first for a workshop in 2017, which was the first time I'd ever heard of deep learning in my life. And I got to see Jan LeCun do a talk. I got to see Terry Tao do a talk. And then I got to come back to IPAM and participate with many high caliber and elite scientists. I did my PhD at Baylor University in the Department of Geosciences. I graduated in 2020, which we all know is a super peak time to be looking for new jobs. I was a NASA postdoc from 2020 to 2022, and I'm now an assistant research scientist with the Global Modeling and Assimilation Office at NASA Goddard Space Flight Center, where I focus on machine learning enhancement of Earth system models and data assimilation workflows to provide data-driven mid-range weather forecasts. My name is Katherine Breen. I go by Kathy. You can call me either of those names. If you could not choose from this list on the side here that are actual names I have been called professionally while using my email, that is my actual name. That has also caused a lot of confusion, mostly on my part. And yes, I have been called Kathy with a K, where Kathy is spelled with a C. This visual, yeah, it is amazing, yes. This visualization is a representation of the Earth as a system of systems. Just like the human body, it comprises diverse components that interact in complex ways. And in our attempts to simulate these processes, we have increasingly complex and energy-demanding algorithms that we're all trying to work with. We're trying to get all of our data to work together. We're trying to get all of our models to work together. And the methods that we're using to represent these systems are changing and enhancing over time. And I'm so excited to see what everyone's doing with that. This is the NASA Earth Science to Action visual that we sort of pass around. And the Earth Science to Action strategy is NASA ESD's response, Earth System Directorate, to the 2017 Decadal Survey, which charged us to pursue increasingly ambitious objectives and innovative solutions that enhance and accelerate the science and applications value of space-based Earth observations and analysis to the nation and the world in a way that delivers great value, even when resources are constrained, and ensures that future investment will pay substantial dividends. So with that super simple mission objective, this is where we sit on the hierarchy of this NASA Earth Science Plan, doing Earth system science and applied research, where we develop the models that will then be deployed to policy and decision makers for them to help make decisions in their strategies. The way that we think about and have always thought about environmental prediction and numerical weather prediction has been in incredibly complex ways, right? In 1922, Lewis Fry Richardson imagined this forecast factory wherein thousands of human workers would manually perform the mathematical steps of weather prediction, each person being responsible for an equation in a particular grid cell. And numerical weather prediction requires breaking the atmosphere into small interacting pieces so that we can make accurate forecasts, which are demanding massive parallel computations. So obviously, we don't make weather forecasts in this way, but here in 2025, we have our forecast factory that is powered by a workflow of global observations, assimilation, model development, interpretation, and communicating those results to our community. And today, I'll talk about how NASA is using machine learning to enhance our ability to do numerical weather prediction in a data-driven framework. So one of the problems that we face in GCMs is that subgrid variability is highly uncertain. And so, for example, some of this uncertainty, and quite a bit of this uncertainty, comes from the representation of processes that are happening within that grid cell, right? One example would be aerosol cloud interactions or the formation of clouds. Each individual cloud is maybe on the order of tens of meters, whereas a 1 degree grid cell is hundreds of kilometers, right? And so that's quite a relative difference. So the problem is that we need accurate parameterizations for the subscale dynamics that are occurring. And the numerical solution is to use our best available theory and data assimilation to do this, which is very powerful. But numerical methods can be computationally expensive, and we have a significant lack of fundamental scientific knowledge or even our ability to observe particular phenomena. And so we use new innovative solutions to leverage patterns inherent in data to make these physically constrained predictions. So the majority of the uncertainty in our climate models actually comes from this representation of, or the misrepresentation, the lack of subgrid variability representation in aerosol cloud interactions. And so that's one of the reasons that we feel so motivated seeing all of these atmospheric models coming and being developed. Would you like to make a comment?
That is a standard version of people who work with large models, but another huge source of uncertainty are mathematical ones.
Absolutely.
I will talk a little bit this afternoon about.
Absolutely, there are many different sources of error. The evolution of numerical weather prediction from the 1950s to today. In 1950, we see the first implementation of NWP done on a computer. In the 1980s, we see the use of statistical methods and improved numerical schemes in weather forecasting, to the emergence of neural networks in the 1990s. In the 2000s, machine learning-based enhancements that are accelerated by hardware. And as we move forward through the 2010s and into today, we start seeing huge models, huge foundation models, start talking about Earth system digital twins and the hybridization of numerical and data-driven algorithms. Just a couple of background slides to make sure that we're all in the same place. Today, and probably throughout this week, we'll talk about reanalyses. What is a reanalysis? A reanalysis is a data set that combines observations with weather and climate models through data assimilation to provide a 3D gridded state of the atmosphere. So it is a 3D gridded product made from disparate observations and our best available background forecasts. This produces a consistent and gap-free data set over time that we use to both power our GCMs and as a benchmark for forecasting. I'll also talk about foundation models today. So a foundation model is a class of pre-trained machine learning model that is intended to encapsulate a large variability of potential downstream applications that could be fine-tuned for. The idea that was put forward in the seminal Stanford white paper was to train models on all different types of inputs, on images and text samples and structured data and unstructured data, and to have that model be capable of contextualizing that information and being fine-tuned for some more specific task in the future. In weather and climate, we see foundation models being developed on reanalysis data sets. So we see the reanalyses used as training data for the foundation models themselves. And adopting foundation models for science requires some additional quality and assurance. We see a lot of these models coming out in publication, but not necessarily a quantitative evaluation with respect to our operational systems. And so at Goddard, we approached this, this work to do a quantitative evaluation of operational foundation models against, foundation models against our operational numerical weather prediction system, GeoSFP. So basic concepts of how a foundation model is running. This is a sample of the likely variables from ERA5 that would be pulled into a given foundation model. Some of them use different variables or additional variables, but this is generally the core set of 5 to 6 3D state variables, and then a few surface level variables to control those dynamics. And generally, we take the atmospheric state at time t, and the foundation model then predicts that atmospheric state at a future time plus a delta. Yeah.
Is it strictly the input is at time t, or is there any like time t minus 1, t minus 2 also, or is it?
So GenCast, out of the models that I'll show you today, there are a lot of these models, right? I'm just going to talk about 5 of them. But GenCast actually does use 2 time steps to then predict the next.
The most just use?
Most just use one to go 1. So we evaluated all of these models out of the box. So for example, I'll talk about Aurora. Aurora actually has 2 releases. There's a base release, and then there's a fine-tuned release that also uses some additional high resolution and actually proprietary data sources. And so we used for example, with respect to Aurora, we used the base version for this evaluation. We wanted to see out of the box how these models compare against our operational system without needing to be fine-tuned. Okay, so we performed 10-day rollouts over 2024, focusing on the months May and December for 2024 for these 5 different models. A couple of things to point out about these models. The majority of these foundation models were trained using ERA5. That meant to do the rollouts, we used ERA5 data for that. Prithvi WXC is actually a NASA model that was trained using MERA2 reanalyses, which is our GMAO product from my research group. Another thing to note is that if you look at the architectures used for these models, they kind of fall into 2 broad categories, either graph-based neural networks or CNN-based, essentially the transformers, but essentially CNN-based networks. And then another thing that I think is really important to acknowledge with foundation models, we'll see some great results that seem very promising, but please note that there's only a subset of levels, of pressure levels. So the full ERA5 data set has 37 atmospheric levels, pressure levels. Here we're only using 13. So while that does cover the range of, say, surface up to, I think, what did I say, 50 hectopascals. That is still a subset of the atmosphere. Yep.
I'm curious, it seems to me that the base architectures that are used for these models fall into, as you said, basically 4 or 5 different categories, right? Either you use attention, transformer, graph neural networks, plus diffusion, or your regular CNN. Why do you think, based on your evaluation of the field, that we haven't had more diversity in architectures, the way that other fields like computer vision or large language models have kind of had more of a ecosystem of architectures?
Yeah, I have a lot of thoughts on that I, are probably more of just my personal opinion.
Yes, that's what I want to know.
Yeah. I think, in some ways, I think this field is moving so quickly that there's a lot of sort of flag polling going around, right? There's a lot of proof of concept work to demonstrate and then moving forward from there. I guess, we have to create benchmarks somewhere. So use the architectures that work and then see what you can do with them. And if you can do something great with them, then why spend more money and more time and more resources trying to come up with a bigger, better algorithm? At NASA, I feel very strongly about this, that we are not really in the business of developing software or of developing new machine learning architectures necessarily. We are certainly in the business of fine-tuning software for science, right? So, I think you're bringing up a really important point, though, that the way that we're making models is the way that we know how to make models, right? There are better models that we can make if we think outside of the boxes that we've built for ourselves. But this field is moving forward so quickly that it's very, very difficult and not as lucrative to take that pause, right? Which is why weeks like this are so important, that we all have the time to force ourselves to take a pause and to think about the boxes that we've sort of built for ourselves, right? So that, I think, is an important discussion question to keep in mind as we're moving forward this week of, maybe what other architectures or what other structures can we provide for a neural network to help us pull out more physically meaningful predictions, right? Yeah. Yeah, thank you. I'm sorry, I didn't get your name. Nice to meet you, Eduardo. Thank you so much. So we did these, 10-day rollouts for these foundation models. They took between 2 and 15 minutes per rollout, depending on model complexity. We did these all in the same container. We used the same hardware, same software, same computing configuration to run all of these. And now we'll talk about some results. So I'm going to show you 3 slides that look very similar, but are showing the same results at different levels of the atmosphere, right? So we compared our foundation model forecasts against GeoSFP over the period of December 2023 to May 2025. I'm going to show you results for May 2024 here. So we did so here we can show the forecast skill evaluation metrics. On the very top is the anomaly correlation coefficient, and on the bottom is the difference or the bias relative to the input reanalysis. You'll see that on the bias section, GeoSFP is actually not shown on that graph. The reason is that we run GeoSFP in a replay mode, and so the bias becomes sort of controlled or less apparent, so it's not as meaningful to have it on that chart. So one thing that I would point out initially is if you look at the anomaly correlations, we see 2 models dominating an anomaly correlation past a lead time of maybe 5 days. And those 2 models are GenCast and AIFS. We also see those 2 models developing quite a bit of bias, accumulating quite a bit of bias over time as we run forward relative to the others. So this is we're looking here at the lower troposphere for geopotential height. So in the lower tropospheres where we're having near surface processes, these are very strongly influenced by the boundary layer and by land and ocean interactions. As we move a little further up in the atmosphere, so now here we're at 500 hectopascals. In the upper troposphere, where we have a different physical system, and yet we see those same performance metric trends persisting at this location in the atmosphere, which...
When you say difference, does root mean square?
This is just a bias. I don't believe this is root mean squared. I think this is just a normalized bias, but I could check that for you.
Okay.
So let me show you.
Right, on the same question, how are you averaging over space in the lower plot?
How are we averaging over space? These are global. This is a global mean.
Okay, so if you have negative and positive errors, would they just average out in this bottom plot?
I guess if you had an equal amount of, yeah. Okay, so what we see is that the overall performance metric trends sort of persist throughout the atmosphere.
Sorry.
Yep.
Can I just follow up? I think that's a very good point, because if you have a model that generates a wave pattern that's just out of phase to your training data or to the truth, then you'll have positive and negative bias, and then that will cancel out. Would that be possible in this analysis?
I think so. I think it would, yeah. Thank you for pointing that out and for explaining that.
I also have a follow-up. I think the anomaly correlation coefficient would reflect when you have something out of phase, it would perform worse, but I think the bottom chart is solely a systematic bias chart.
Correct.
So it's only showing, is it always higher or always lower? And it'll be 0 if they cancel out, but the ACC will be a lot lower.
That's a very good point.
Sorry to also pile on, but which AIFS is it? Is it the CRPS one or is it the deterministic one? I'm trying to see if is it more similar to GenCast or to like Aurora?
It's the base model that the whatever AIFS was not fine-tuned. Sorry, I'm having a little bit of trouble hearing you.
Is it the CRPS one, the one that's stochastic, or is it the one that's deterministic?
CRPS.
Okay, so it's similar to GenCast.
Yeah. Okay. So we see some architectural implications here that, in general, the graph-based models capture the anomaly patterns better, but they exhibit a lot of amplitude drift, right? They're rapidly accumulating biases with longer lead times. The CNN or transformer-based models are more tightly coupled to the reanalysis used for training and seem to produce local spatial consistency, perhaps resulting in slower amplitude degradation. I'm now wondering if perhaps some of these artifacts are maybe more related to phase, but that could be something that we should investigate a bit. Yeah, DJ?
Yeah, the other thing you might be seeing with the GenCast and AIFS, assuming that's both their ensemble versions, is
Correct.
the fact that they're on an ensemble average versus everything else being deterministic numbers.
Yeah, absolutely. So that's an important point also, that we see GenCast as being such a great performer because we're looking at the ensemble. Yeah.
I think for GenCast, it's also important to keep in mind it's using a stochastic differential equation to do the rollout. So its inference is quite different when you have diffusion. So the rollout, because you're doing that, is going to amplify the errors faster during the inference stage. So not necessarily a artifact of training.
Yeah, that's a good point. Yeah, thank you for bringing that up. I want to make sure we're doing okay. So now I'll show you some scorecards. So I'll show you 3 scorecards for different foundation models we evaluated. And so this is evaluating a foundation model relative to GeoSFP. A solid red color means that the foundation model performed significantly worse than the operational forecast, whereas a solid green would mean that it performed statistically significantly better than the operational forecast. So here we're looking at 3 latitudinal bands, northern hemisphere, the southern hemisphere, and the tropics. We see 1, 2, 3, 4, 5 different 3D atmospheric variables, and then as well as sea level pressure. And you'll see 2 different metrics here, both correlation and RMS, and they are shown for the first 5 days of the rollout at 12-hour intervals. So this is the scorecard evaluating Prithvi WXC against GeoSAF-P. Prithvi WXC is the only NASA model. It's the only one trained on MERA 2 reanalysis. And unfortunately, we don't see it out of the box comparing very well or performing well against our operational forecast system. It's important to note that Prithvi wasn't intended for use as a forecast model, but as they say, a rather robust estimator of the state. But what we can confidently say is that we don't recommend Prithvi for scientific applications without fine-tuning first.
Without?
Yeah, I would not recommend using it without fine-tuning. Yeah.
Was this at all tested to see the difference between its performance in places that are a lot more observation dense, or is it only global average that we're going to be looking at?
Right. So, so we're using the reanalyses, which through the data assimilation algorithm, like a lot of the sort of biases towards areas that have more observations, that algorithm is trying to remove a lot of those biases and only use the highest quality observations. So I think your comment is really leaning towards overall science is biased towards places where we have lots of observations, right? And so we, at a minimum, have better benchmarking. Right?
I'm so sorry.
That was actually incredible timing. Let's look at another scorecard. So this is for Aurora versus GeoSAF-P. So we see a lot more green and not as much red in this picture, which is really great. Remember I talked about how we're using only the base model for Aurora and not the fine-tuned version that they have. So the base model was did not include latitudinal weighting during their pre-processing. They included it in the training algorithm, but the pre-processing did not explicitly add in latitudinal weighting. And so we see actually very good performance really closer towards the poles, and yet not as good performance in the tropics because the predictions are biased towards the pole due to not having the weighting. This problem is fixed with the fine-tuned, I think it's like the LoRa release of Aurora. We chose not to use that at NASA because it required getting some proprietary data sets that we just don't do that. Okay, we have enough data. Okay, and here's the GenCast model against GeoSAF-P. And as mentioned, probably likely because of the diffusion or ensemble nature of this forecast, GenCast outperforms the other foundation models evaluated in terms of forecast skills across variables, across pressure levels in the atmosphere, and latitudinal bands across the globe. So we are actually doing some fine-tuning applications of GenCast right now to enhance our operational forecast system. Yeah.
In kind of a similar vein of the prior question, have you guys looked at just in general the spatial structure of the skill? Like, are there places that GenCast does well, the operational model? Like, I feel like we always get these scorecards, but I always want to see, the map of where these models performing well versus more limited.
Mm-hmm. No, we haven't, not for the purposes of this presentation or for this this initial sort of effort, right? This was these results came out of a scientific task group or an STG that we had at NASA that ran for, I think we had maybe a year of funding, and so we were able to get scientists between 3 different research groups to perform the analyses for the results that you see today. And then what we've left it up to now is for, now we're presenting this to other scientists or talking to other NASA researchers and getting people to apply foundation models to their research so that I think we can answer more questions like this. So I think we are doing the benchmarking essentially for future fine-tuning work. Yeah.
But it's clear that it has a little bit more trouble in the tropics.
It does have a little bit more trouble in the tropics. That's true. I don't think that we can, have incredible expectations of perfection for everything, but this was certainly the best of the bunch, right? Yeah.
We're 70 and 10 millibars not evaluated on here because I noticed on all the charts there's no scoring there, and I was curious why.
Yeah, I think we just tend to not have as much data at those pressure levels, and I forget what software it is that makes these scorecards, but it's like a piece of software that, a NASA scientist wrote like 40 years ago, to be totally honest, that to reverse engineer and like fix that little error, I think would take a support scientist like 3 weeks. I'm being hyperbolic, but that's why, and I'm sorry, yeah, that is kind of an artifact that I prayed nobody would notice.
Yeah, it's one of those where a lot of these models struggle at that level, and be curious to see how these compare.
Yeah.
I was also interested to see that when you showed Aurora, that it was doing quite worse in both the tropics and the upper levels.
Yeah.
Because in the original paper, it was, at least they were claiming they were doing better. So this is an interesting result.
But I think their original paper was a lot of their results were looking at the fine-tuned model, not the base model. Yeah.
Good catch.
So I do really want to point that out, that it's not that these publications have misrepresented their results or their work. It's that they are, presenting a product that we at NASA couldn't use operationally because of various concerns. Okay, yeah.
What is fine-tuning usually done on? Is it another data set?
Right. So, it's when we say fine-tuning, we're basically just talking about transfer learning. So you could use other variables from a reanalysis. You could use a different reanalysis. You could use observations. It's using additional data sets to get new information for a new target, right? So I think, we're talking to people at NASA about, various fine-tuning applications that they could do right now. And what a lot of people want is a different variable, or they want more vertical levels. The vertical level problem is really difficult to solve computationally because we just don't have those types of resources, right? Even for Prithvi to be developed, I say that's a NASA model, but it wasn't developed using NASA computational resources. That was a collaboration with IBM, and they actually trained that, I believe, on DOE Frontier. So, that is another reason why I say that NASA isn't really in the business of developing these sort of not to overuse the word foundational, but these sort of like foundational models or foundational pieces of software that, private companies or, Google, whatever, they have the computational resources, they have the manpower, they have a room of, 20 PhDs who are all working on this one problem. So, and they pay them really well. Okay, so key takeaways of the foundation model assessment. GenCast is clearly outperforming the other models in our short-term forecasts for common variables of the atmospheric state. The caveats here, as mentioned, you don't get all atmospheric levels as output, only the 13 or 14 levels that it was trained on. For GenCast in particular, you can only generate a forecast at 12-hour intervals. All the others are at 6 hours. And the full resolution requires quite extensive resources, which we happen to have. None of the AI models sort of out of the box predict important diagnostics like precipitation, although I do know there's quite a bit of work right now in fine-tuning models for fine-tuning foundation models for precipitation. There is a bit of a delay, more or less, but the one issue that we did run into that I would bring up if anybody were to try this work on their own, a lot of the pre-processing is internalized in the models. And so you actually don't need to, say, do pre-processing for ERA5 before you run it through the model. But that does also mean that the pre-processing isn't necessarily explicitly transparent. And so it can be difficult to reproduce if you were trying to do that on your own. Okay, I'm going to shift gears in a moment. Does anybody have any other questions or comments on foundation models? Yeah.
Yeah, have you looked at metrics that take into account the price of inference per model? Because these models have a very, very big discrepancy between GenCast, where you need to run the model autoregressively like so many times for just one step, and models that are just a plain backbone. So did you look into kind of price versus performance metrics for these?
A little bit. So we ran some timings. Some of them. So GenCast takes more resources. It takes more time. So to do a 10-day rollout for GenCast takes about 15 minutes, whereas for Aurora it takes about 2 minutes. If you wanted some more, if you have more detailed questions about the specific configuration that we used, I can get you in touch with the people who built the container, and they can probably answer some questions for you. And I'm really excited about the hand raise robot. How do I call on it?
They can hear you.
Oh, okay. Yep, please go ahead.
I take it that's for me on Zoom.
Yes.
So one of the criticisms of early papers was that measures of activity tended to drop or weren't included. High ACC and low RMS can happen just by smoothing the fields. Did you check whether the variance was being maintained by some measure as a function of forecast time?
I saw a lot of people nodding along. I actually am having a really hard time hearing. Could somebody repeat the question for me?
David was saying these are evaluated on smooth fields, and you can get good results on smooth fields by smoothing, right? And it looks a little different if you look at more fine-grained local evaluations.
I see. Yes. Yes, that's a very good point. These are definitely some initial results, and I'm definitely hearing that people want to see more global variability. They want to see how the uncertainty varies globally in these types of results. So I think we should start preparing those types of visualizations as well. Okay, so now we're talking to a lot of people about fine-tuning these types of models. Yeah?
I just had a comment about, before we step off foundation models. You mentioned that it takes a beefy GPU to run these, and we found the same thing. But the nice thing that we're trying to explore at Sandia is that you only have to download the foundation models weights once.
Yeah.
Whereas if you want to download ERA5, they throttle the requests based on how large they are and things like that. So it is kind of exciting that if we build trust in the foundation model to at least reproduce what it's been trained on, ERA5, maybe we could use it and the 10 minutes it takes to do a rollout instead of having to wait the 3 hours to download ERA5.
Absolutely. So, to do this work, we had to download a bunch of ERA5 data, and guess whose job that was, right? Downloading data, we all did that in grad school. We all do that for our whole lives. Like, that's just a little bit of grunt work that shouldn't take 5 months. But a lot of people try and download ERA5 data, and so there's there's a bit of a bottleneck there. I was trying to automate the process to get the data downloading without me having to sit there and monitor it. And I asked our IT people, I'm trying to figure out how to automate this thing, and they said, Kathy, you are never going to be able to automatically download from an internet server onto a NASA computer. It was a very strongly worded email, and I put my tail between my legs and I stopped trying to automate that process immediately. Anyway, that's a very excellent point. That, we think about, I'm going to talk about data assimilation in a moment, and I work for the Global Modeling and Assimilation Office, right? There are a lot of people whose bread and butter are numerical algorithms. And I think that there is a bit of maybe fear or concern that machine learning is coming to take our jobs, right? We hear that a lot, or to replace the legacy or careers of people. And I think that we are underestimating the success of numerical work that has been done so far, and I think we're overestimating the effectiveness and maybe the trust that we can put into machine learning solutions. I think that we use these types of solutions to enhance what we do currently operationally. Can we use foundation models to make ensemble members faster so that data assimilation algorithms can run faster? Can we use foundation models to get around latency issues? Can we enhance our current workflows by reducing computational cost in one way or another? I think we've talked about fine-tuning enough. So I'm going to talk a little bit, really a little bit, about something we're calling neural state estimation. And if you haven't heard that term before, that's totally fine because I made it up. And we wanted a term so that we could talk about like machine learning for data assimilation, some kind of obs to state or obs to forecast machine learning emulation. And so we made up this term for it. And now when I say the term, I have to explain this whole thing, and it's actually not faster. But that's fine. So now we're working on some initiatives to look at how can we make a gridded 3D representation directly from observations, right? And so there are lots and lots of papers that do this. I'm actually going to skip over this wordy slide. I'll make my slides available. There are lots of groups that are doing this right now. And so similar to how we did that quantitative evaluation for foundation models, we started looking at, can we do the same or similar thing with these NSE type models? And so we looked at these models and we pulled some of their code from GitHub onto our HPC system at NASA. And there are some issues, right? I'm just going to skip ahead a little bit. One of the biggest problems in using these models is that they're largely developed off of whatever data people have available at the time, and not necessarily the data sets that we use for science, right? There's a lot of proof of concept work going on. So for example, Artivark weather is one of these sort of neural state estimator models. And here I'm just showing the data sets that they use in their training algorithms. And then I'm comparing that against the data sets that we use in our operational framework. And there's very little crossover between the data sets they're using and the data sets that we use, which means that in order to use their model, we would have to download a bunch of data sets that we don't use operationally at NASA, and we make a lot of data at NASA. So that doesn't really cross over very well. A lot of these data sets are also proprietary, and so getting access to them is somewhat limited as well. And they're not, these models aren't always developed for science by scientists, right? They are developed by computer scientists or by business people who have very good ideas, but aren't necessarily developing them for scientific applications and may not have domain expertise. And so we've started now to experiment with developing some of these NSE type models, and we're still really early on in the work and the conceptualization, but that's sort of the next evolution that we want to move into. And again, not using machine learning to replace data assimilation necessarily, but how can we enhance these workflows? And so I have a couple of discussion questions just to get your minds sort of thinking throughout this week, that I think that these are some very common themes that I certainly am questioning a lot right now, and that I was questioning a lot when I looked through the schedule for this week and looking at all of your talks. So for that, I'll show you my final slide that I spent way too much time making. Just wait.